Introduction to Testing of Materials by former Professor P.K. Datta, Material and Metallurgical Engineering Department, Jadavpur University, Kolkata. In lecture 2, we will discuss Brinell hardness test. Brinell hardness test, in principle, is a very traditional hardness testing. It uses a hardened steel ball or tungsten carbide ball indenter of diameter D and pushes or indents with a predetermined load P on the test material surface for 30 seconds and then releases the load. A spherical impression develops on the test surface and the diameter of the indented circle, known as indentation diameter, small d, is measured by a microscope. Using the formula, BHN can be found out. Brinell hardness number can be found out. This is given by applied load divided by spherical surface area of indentation in millimeter square. And in formula, this is given by 2p divided by pi capital D within bracket capital D minus under root of capital D square minus small d square, where P is already told. This is applied load in kgf and capital D is diameter of the ball indenter and small d is diameter of indentation we made on the surface of material in millimeter. Now, the applied load P, how we will determine the applied load P? It depends on type of material. For example, steel, this is given by 30 d square, where d is the diameter of the indenter, hardened steel ball indenter or tungsten carbide indenter. For steel, 30 d square, 10 d square for copper and 5 d square for aluminium. So we have to calculate what will be the applied load for our tester, and this is will be calculated in using this formula depending on the type of material. For a standard Brinell, the ball indenter diameter is given by 10 millimeters. It's a huge, large ball. And it needs high loads, around 3000 kg. 10 square is 1000, 10 square is 100 into 30, so 3000 kg is a huge load. Only the plant or a big factory can accommodate this. So in a laboratory, we use generally non-standard Brinell, where the diameter of indenter is 2.5 or 1.5 or 1, dependent on the type of the lab we are using. Now, BHN calculation example will be enough to understand it. Suppose we are taking a problem, a BHT, Brinell hardness tester, uses 1 millimeter tungsten carbide ball. Find out the applied loads. Now P is equal to 30 d square, 30 into 1 square equal to 30 kgf for steel material, 10 kgf for copper and 5 kgf for aluminium. Now, an example, how can you determine BHN? Next problem. A soft steel can sheet came for testing BHN in this laboratory. If the diameter of indentation is measured 630 micron find out BHN of the material. Now solution. P is equal to 30 kgf for steels. So root over capital D square minus small d square, that is under root of 1 square minus 0.6 square is equal to 0.78. Now we know 1000 micron equal to 1 millimeter, so 6630 micron is equal to 0.63 millimeter. Now the denominator 1 minus root over 1 square minus 0.60 square is equal to 0.22. So if we now put these values in the formula, BHN is equal to 2 into 30 divided by pi into capital D1 into 0.22. It comes out 85 kgf per millimeter square. So BHN we will write 85 BHN. It is more or less very soft steel. Now, word of caution. When you start the Brinell hardness testing, it is good for castings. Particularly, grey caster and foundries prefer BHT, Brinell hardness tester, as it uses apparently large indenters which can give average hardness. For primarily heterogeneous materials like grey cast irons, having very soft graphite and hard cementite. Graphite is very soft. You use in pencils the graphite for writing, but cementite is a very hard. So when both of soft and hard phases, that is material constituencies, are in the material, we can use BHN. BHN can be very much suitable for medium hard materials. As for soft as well as hard materials, sinking in or rigging up defects are common. So for medium hard materials, BHN is generally used. It should not be used for very soft material like lead, zinc, etc., which are very soft, or it should not be used in hardened steel because the ball is already hardened indenter. So in those cases, there is a chance of defect. This is so far about the Brinell hardness test, and we will continue this program for next lecture for Vickers hardness test.